like to introduce our industry guest now. This is John Mellot. He is a Chief Engineer and Fellow of Mercury Systems and Secure Processing. I think this is the first time we've had someone coming to talk to us from an industry which has an awfully high level of documentation, regulation, and certification. But this kind of problem also applies directly to medical, to aerospace, to a whole load of other fields as well as defense. So let's give John a good welcome and look forward to hearing all about Mercury.
Thank you. Good afternoon, everyone. Thank you for coming today. I appreciate it. I know you have to be there, right? You can see I've been up for a long time, so I'm double fisting my hydration, because hydration is awesome. Anyway, I'm going to talk first about, how I got here today. Obviously I'm a senior level person at Mercury. Been doing this and other things for a long time, right? And the how chips change the world really appeals to me as a topic, actually, because what I'm going to start talking about is in my youth, my desire to change the world, right? And how I wound up in the semiconductor industry because I felt like that was a way that I could change the world. And it's been a long, strange trip in some ways. So, with that, I was, like 8 years old. My father was working at an insurance company, and took me to the office for some reason. I have no recollection of why, but sat me down in front of a terminal connected to a mainframe computer, kind of like, that guy right there, IBM System 370. It was probably 1976 or so, something like that. And that was my first taste of computing, because, we didn't have home computers, none of that existed, right? There were no computers in your coffee maker, no computers in your light switches. The world was an analog world. That was just enthralling to me. So a little bit of time passed, and before long, I had a home computer. Oops, wrong one. That one, that guy right there. Got one of those, and here I am, 10 years old. I start, learning to program it. I want to, program some cool stuff. And pretty soon find out that, BASIC, which is, what I had to program it with, was not good, right? Too slow. I was trying to do things because, I play games on it too, right? And it's like, how do you do the stuff in the games? Stuff you write in BASIC is, terrible, slow. So, kept on going. So I picked up assembly language. Before too long, other computers started to appear in my life. Some of you have probably seen pictures of these things too. The Apple II there. That was a popular computer. By the way, it'll kill you, right? These 8-bit computers with 32 kilobytes of RAM and 100 kilobyte floppy disk drives. I mean, you spend $1,000 on a rig, and this is in those days dollars, right? These were really expensive, even more and more started to appear in my life. Eventually there was a machine that ran CPM, control program / monitor. It's like an early operating system that was kind of like other operating systems you see today. It actually run on different computers from different manufacturers, but really oriented for people doing business. It's word processing, VisiCalc, which was the first spreadsheet program, that was kind of thing. In school, one of my schools, the TRS-80, made by Radio Shack under their Tandy brand. Also a Z80, but ran a thing called TRS-DOS, or We affectionately call it the trash 80. Um, you got it. So, and you would find all these interesting things you could do. You would explore these things, right? There's a certain amount of lore. There's no Google or anything to go learn anything. You have to figure things out on your own. A certain amount of reverse engineering from a software perspective. Incidentally, besides floppy disks, these things also could use cassette tapes for data storage. And the cassette drives, right? Drives is really, an audio tape recorder would have a control. The computer could turn the drive on and off to make it, start reading or start recording. Well, that was an electrical mechanical relay. Well, before long, you learned you could write to a location memory to open and close that relay and, make a little click, right? Well, you can click it at various speeds and play music. This works great until, they're only good for so many times. And then snap. Do this on school computers. Did I mention that? Mainframe computers continue to be in my life. This is an IBM 3270 mainframe terminal. My school district at the time had these. Again, connected to one of these. Had first IBM PCs. 2 floppy drives, 256 kilobytes of RAM if you were lucky. Then bigger computers, IBM or DEC VAX, digital equipment, super mini computers, which you again use timeshare terminal. Later in life, Sun Spark Station, full Unix computer. Yeah, you could have multiple users on it, but generally speaking, you were using it yourself. First chips I designed were, on computers like that. Over the course of, from my youth through high school and, into undergrad and finally grad school, there's a humongous amount of evolution in computing that happened. And it really did. It changed the world. By the time we got to here, Sun Microsystems, their motto was, the network is the computer, right? So before, with all these things, even these guys, no network, right? At some point, Al Gore says he invented the internet, and there we are. Sorry. Another one for the old people in here. I apologize. One of the things in my youth, I quickly realized, computers are cool. And guess what? They're full of chips. You laugh, right? But, maybe that's not the obvious thing, right? It's like, computers are cool. Okay, I was doing software. But the really interesting part is, what the heck makes a computer go, right? And there are so many differences between computers, so many manufacturers with so many differences at the time. This is an IBM PC motherboard, which, as you can see, is covered in chips, right? And chips in the sense that you think of these packaged parts. You got like a whole bunch of memory here. The CPU is right there. That empty socket. You had to pay extra if you wanted to do math. No, it's good. No kidding. And that existed for many generations, where you had to buy a math coprocessor if you wanted to do math. If you want to do math quickly, you could do math very slowly using that CPU. And you look at something like this, and you can see stamped on the motherboard that this could be configured between 64 kilobytes and 256 kilobytes of memory. You guys know what kilobytes and megabytes and gigabytes are, right? It's not a foreign term. This is very, very tiny by today's standards, but people could do useful work with these things, right? But at the same time, that we were in the early days here where these memory chips. I mean, you can count how many sockets there are, and you think about how many, basically 256 kilobytes. A lot of chips to get to that much memory. And then you see a lot of chips like this that are on here. this is what we used to call small cell integration chips, right? This is, 1984 is when the IBM PC was introduced. And you can tell from the wires on here, this was probably a very early motherboard. They had mistakes, so they had to put wires on, right, in the original design. They'd fix the printed circuit board layout later, but that's the way it is. And a chip like that's got maybe 16 transistors on it. That's it, just 16 transistors, right? You get a lot more transistors in something like this memory chip. The CPU is probably maybe 100,000 transistors at that time, right? But just absolutely, to me, fascinating. Bit of technology here. Anyway, we'll move on. So, you see where I'm going. Computers changing the world. Computers are full of chips. Therefore, the chips are the important part in my mind. Oops, I went backwards. We'll go forwards. Come on. There we go. And I just said, the CPU. The CPU, everybody said, what's a CPU? It's the brain of the computer. That's kind of the metaphor everybody would use in the 1980s, right? And so many CPUs out there. I mean, I said there were all these different computers, right? They all had different CPUs, right? And there's so many people manufacturing different CPUs, and it ranged from the very big stuff that IBM was making, the mainframes that cost, millions of dollars, right? And they'd run bigger applications like payroll and, business applications usually, although, there was some science and technology work being done with those. You had smaller processors, these are 8-bit processors, that today, 8-bit processor might literally be something that's in your coffee pot. It's, related to the clock that, turns it on for you if you, set it. And those cost real money back then. And those were found things like, Apple IIs and Ataris. And, the Zilog Z80 was actually a very popular processor, widely used. Interestingly, a derivative of the Intel 8080, which I didn't list here because actually the Zilog was much more popular at the time. That ran things like the Trash 80 I mentioned before, and then various other computer manufacturers that ran CP/M. 1984 comes along, and you get the Intel 8088, which is a processor that's sort of 16 bits, but not quite. And how did IBM wind up using that processor? Well, they wanted to use the Motorola 68000, but Motorola was late. So they switched to the Intel. And had they not switched to the Intel, we'd probably have this really big company worth billions and tens of billions of dollars called Motorola, and we probably would not have an Intel in the world at all. So, dumb luck, a matter of, weeks or months is how that happened. And, 8088 begat a whole series of things that eventually, because, they discovered you couldn't trademark a number, they switched to calling it Pentiums and Xeons and, things like that. And I could keep on going, right? A whole bunch of these things. But, the really interesting thing about the CPUs at the time is that there was a human behind every one of these, right? There was a guy named Gene Amdahl at IBM, who was the father of that mainframe architecture, right? And everybody said Gene Amdahl is the inventor of the IBM thing, right? There was a guy at MasTec who was the father of the 6502. Intel, it's a little bit murkier, right? But, you could kind of go down the list of these things. And there was a guy who, was somehow changing the world by creating a CPU, right? Which then created a computer. And then, because of the characteristics of that computer, somehow that was, providing, incremental value versus the other one, right? So that a 68,000 CPU is a 32-bit CPU, could do so much more than an 8-bit or 16-bit CPU. So that opportunity to, continue this rapid evolution of these things and ultimately their applications, super appealing. And of course, programming, because like I said, I started off doing software, right? And they're plethora of languages. Today, you guys probably, if you've programmed at all, it's probably been, I don't know, what the heck they teach, like in the high school these days. Um, yeah, yeah. There you go. They're still using Java. Okay, great. But back then, BASIC kind of came with everything. Like I said, I very quickly switched to assembly language. And I program assembly language on everything I get my hands on. Because to me, getting bare metal with the hardware was appealing. And in doing so, you learned a lot about the hardware and the CPU architecture. And forgive the picture, it's actually from something that's not any of the things I showed you before. So, by the time I got to college and was actually taking, university courses, I had, a lot of understanding of CPUs, CPU architecture, what made some good for some things, some bad for other things, and so forth. And then in the meantime, and this one, I'm throwing this in because this was also very motivating for me. Supercomputers were really changing the world. And you look at the Cray 1, introduced in 1975. And that picture is from a museum, by the way, and you can definitely find these in museums. And some of them will even let you sit on the padded bench that goes around it, because that's where the power supply and the cooling is for these. And these things are this tall and this wide. It cost, millions and millions of dollars back in the day. At Cray 1 in 1965, 160 million floating point operations per second. Sounds like a big number, right? A whole bunch more Crays later. The last Cray before Cray went out of business, 1994, Cray YMP, 154 gigaflops, So that's, it's literally 3 more zeros, in the course of 20 years, right? 3 orders of magnitude, 1,000 times faster. And there was one person who was the face of Cray Computer, Seymour Cray, right? Completely famous. Here he is producing computers that are being used for weather prediction, modeling the explosion of nuclear bombs instead of setting them off to understand if they're going to work, which, okay, maybe you don't like nuclear bombs, but it's a heck of a lot better not to be setting them off. We started to actually simulate nuclear bombs instead of setting them off, right? And this one guy is like the architect, the chief designer of the Cray computer, right? You guys have all heard of Moore's Law, right? So, Moore's Law is still in effect here, and that's, part of the reason why you went from that to that. But, 25 years later, iPhone 11 surpasses the Cray YMP. You could buy one and put it in your pocket. Super awesome. There you go. And that's 2019. So what you have now surpasses that by probably a couple more zeros, I would bet. So what I do here, I chose an educational path to suit my aspiration to change the world. So when I say that, the title of this class appeals to me, this was literally the logic in my head at the time. So I got a BSEE with a minor in math. I got and I actually, as an undergrad, designed a chip, had it fabbed, right? Tested it, all 9 yards. As an MSEE, I worked in computer engineering, but one of the things that became apparent to me at that point was that the general purpose CPUs that we talked about before, that was narrowing, collapsing. Intel and Motorola basically owned that for the microprocessors, which was really where the future was going to be. It wasn't going to be in the big irons at IBM. Digital equipment was kind of on its way out, right? The VAXes, those mini computers. So where in the world can I do, super computing kind of problems? Signal processing for me was that place where I identified the opportunity to change the world, as an individual, contribute to that, right? Where I could still felt like I could make a difference rather than being part of some behemoth like an Intel. My master's thesis was on the implementation of a thing called a systolic array, which was a kind of way of doing very parallel computing for fixed algorithms that were commonly used in signal processing. And I actually implemented one of these in a 0.8 micron CMOS chip, right? So, and back then we called it pushing polygons, right? Literally drawing the layout, not specifying it in some programming language and having it kind of spit out the back end. In my PhD work, I specialized in computer arithmetic, and again, focused on signal processing because signal processing is arithmetic intensive, and exploited all kinds of interesting tricks of math, right? Remember that minor in math? That actually played into that quite a bit, and a whole bunch of other tricks, and then did a dissertation on a thing called very long instruction word processors aimed at DSP, not general purpose computing. You don't see those anymore. I don't have a picture of it anymore or actually have it, but the first computer I built looked kind of like this one, where, it was wired together by hand. I built it in my last year of undergrad, right? And, people still actually do build some things like this, but you don't see that very much anymore. You guys can quickly and cheaply get printed circuit boards made, which is awesome for you because this was a lot of work. All right, so, while I was in grad school, I'm struggling with the problem of how to get the innovation to the world, right? I, as an individual, am not going to go start a chip company to make digital signal processors, right? And the other thing that was happening is the dynamics of how chips were being made was changing. So a thing called ASICs, application-specific integrated circuits, in the early 90s, that was, booming, right? So people were building custom chips to meet the needs for their particular thing. So if you're Ericsson, you were making custom chips for your cell phones, for example, right? And you were doing it through a methodology called ASIC. And the first ASICs were pretty small, and an individual person might be the person who designed it. But as time went on, and you guys are all aware of the ongoing march of smaller geometries for fabrication and higher capacity in chips. What happened is those chips suddenly became too much for any one person or a small team of people to design. What's more, the things they were trying to do with the chips were more complicated. They needed additional functionality that maybe they didn't have the expertise to design or didn't want to. This creates an opportunity to go buy a function, go buy a design for a circuit, drop it in, use it. It's not your value add. Your value add is somewhere else in that design of that ASIC. So, my aha moment was, let's supply specialized content, right, at signal processing in particular, as what we call semiconductor IP, or intellectual property, which is a fancy way of saying that we're creating designs for circuits that we were going to sell to many different people, right, making chips, and enable them to realize their end application. And when I say we, I mean this was mostly me, figuring out how to do this. I became involved with a small company called the Athena Group in my grad school days, and started to work to develop this concept. And the first people we approached about this, we quickly realized we didn't have a way to deliver the designs, right? We could talk about this is how we would design it, and yada, 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 but how to package that and get it in their hands and make it so that it wasn't adding a person to your design team, but just literally delivering the design and having them drop down hadn't been worked out yet. So this took a little bit more time to work out. And at the time, the company was selling signal processing design software, right? So it's kind of like MATLAB, but different. And it was actually being used quite a bit to design things that were doing signal processing in the program, commercial digital signal processor microprocessors. The real aha moment here was, that was kind of a finite market, and we wanted to go for something much bigger. And I say we, time the company was about 2 full-time employees. I worked with the team to develop the funding to really pour on the gas and solve that problem, and entered the market and formed partnerships with ASIC providers, the companies that were providing the services necessary for other companies to go fabricate the ASICs. And they were starting to provide IP, like microprocessor IP, provide memories, the actual underlying, what we call cell libraries, so the AND gates, the OR gates, et cetera, that all went to the design of that. And we were selling digital signal processor IP, and having some success with that. In 2000, we were invited by one of our customers to look at cryptography, and signal processing IP. We're invited to look at the problem of cryptography, right? Security, because public key cryptography is very compute intensive, and we were very good at building very high performance compute functions and signal processing. And our first engagement, we delivered an IP core solution that, if you break down the arithmetic, was doing 2 trillion arithmetic operations per second using only 1.8 watts of power, which is an enormous number, especially for 2000. Then the dot-bomb happened, which is a whole other story. Anyway, the key to success here was figuring out a way to provide significantly differentiated content that gave our customers competitive advantage, to the point that they didn't want other competitors to find out they were using our stuff, because then that would level the playing field, which was pretty awesome. Felt good, right? Changing the world, right? A lot of things happened. Fast forward 20 years. I led successful exit of Mercury Systems along with my team. When I say exit, I mean selling the company. Mercury bought Athena, right? And here I am today. 10 minutes, thank you. So we're going to talk about Mercury now. So this isn't all about me. I got better slides that I borrowed from the corporate deck here, at least a couple of them. So what does Mercury do? Mercury, is really about providing mission-critical compute, and other semiconductor-based solutions for signal processing, analog processing, even displays, at what we call the edge, meaning, out there in the field, where there's not a good network connection, right? The cloud, there's no cloud at the edge, right? Or the cloud, your connection to the cloud's terrible and unreliable. And, we're really an aerospace and defense business, right? So there's your professor's point, a highly regulated, you might say, is absolutely true. And, so how does Mercury fit in the semiconductor ecosystem? We fit in a lot of ways, and this was kind of a big jump for me, right? Because here I am, for 20 plus years, 25 years doing semiconductor IP, right? I'm delivering files to my customers, right? Mercury, Mercury delivers things, right? And and they do everything in between that thing and all the way back to here, because we're still delivering semiconductor IP. Companies like these guys, they'll buy our IP and use it, and if you use some of their chips, you might be using some of our IP. We design chips, we package them. There's a couple examples of chips that we've here are chips that we design, chips that we've packaged, that we got the chips that are in this package from somebody else. We build circuit card assemblies that have chips on them, and the boxes, right? And when you talk about semiconductors, people think about the very, exciting, I do design, look at these big multi-billion-dollar wafer fabs. What comes out of the back door of a wafer fab? Wafers. What can you do with a wafer? Hang it on a wall? They're really cool to look at. But yeah, you need to package them, right? You need to get it here, and there are other people that do this, and this stuff is hard, by the way. This is hard too. This stuff is also hard, right? You got to cut them up. You got to get them all in this package. You got to put sometimes multiple chips in a package. You got to test it, make sure the darn thing works. There might be billions of transistors in here, right? And then somebody's got to do this. I got to design this card. They got to go manufacture this card, right? And then you got things that, multiple chips that have got, millions, billions of transistors on them, right? And you got to make sure all that works. And oh, by the way, this is not for Mercury. These are not sitting in some nice air-conditioned data center. These are in the back of a truck. They're in an airplane. They're on a space vehicle, right? They're on a naval vessel. We're getting sprayed with salt water. All kinds of things like that. And they got to keep working, right? And this is hard work, and it needs a lot of people with a lot of different talents. And so, what I'm here to tell you today is, you know the Intels of the world and the Qualcomms and the Apples that are all, very, marquee people making chips, right? But there's this whole how do you deliver the application to the world, right? That adds a lot of value, because if you only got to here, there's no value. This thing is useless until it gets to here, right? And so, you don't have to be an electrical engineer. You don't have to be, a software person. You can be a mechanical engineer. You can be a materials scientist or a materials engineer. You can be a systems and industrial engineer. All these disciplines, all the engineering disciplines contribute to getting these things out the door, right? And there's a lot of opportunity for you. This is, all really part of the semiconductor value chain, right? To get to this. And so as you consider your potential career options and, a semiconductor line industry, I'm sure some of you are going to wind up here, right? But, consider here, because there are hard problems. When we talk about chip packaging, right? Today, there's this huge multinational infrastructure to get from, the wafer here through the package. And now we're packaging many different chips, heterogeneous chips. So it might be a processor from one company and an analog to digital converter from another company, all winding up there to get to that. So you've got a lot of opportunity there to make a difference. And Mercury does in fact do this. We do all these things, right? The circuit card assemblies, as I said, super hard for all kinds of reasons. Thermal. This is a very famous graph. It's been around for quite some time. It came out somewhere around here, right? And the observation was, geez, these things are getting really hot. We're at the density of a hot plate. we're projecting we're going to be at the power density of a nuclear reactor here, and it's going to be like a rocket now. So here, and we're kind of like oh, we're in real trouble problem here, right? And I can tell you, we absolutely have that problem today. The advanced processors we're getting are super, super hot. And how we cool them is, a really super interesting problem. And guys like Mr. Shorey over here, you know, Director of Mechanical Engineering for Advanced Concepts Group, is actually defining our thermal roadmap for the future. How we cool them. And it's not just the thermal. I mean, all these things I talked about, shock, vibration, that IBM PC motherboard I showed you, if you put it in any of the environments we put these things in, they just break, right away. So, lots of interesting things there. And with that, I think I'm about at time. Just want to throw some stuff out about Mercury, so you have Mercury in your mind. Mercury's website, mrcy.com. You can learn a heck of a lot more about Mercury than we've talked about today. But we're not a huge business. Around 2,400 employees. We are distributed enterprise with many locations across the United States. And we do have opportunities for you as students to engage with us. We do have an internship program, co-op program. We actually do have an office here in West Lafayette. And certainly for interns and co-ops, there may be opportunities for you actually to continue working part-time during your fall and spring semesters. So keep your eyes out. Mercury is definitely very interested in Purdue. It's one of our 5 defined focus universities that we're engaging with, and we're very interested in engaging with students and bringing them to Mercury to help us solve these problems. And with that, Sophie. Thank you.
Thank you very much. Now, we normally have about 10 minutes for questions. I don't know, do you have any time after class to stick around?
Absolutely.
Oh, wonderful. So, anyone want to be first? Well, while you guys are thinking, I have a question from some of the lists we collected a bit earlier.
Okay.
How do you balance the massive processing demands of modern kind of AI and edge systems with the size, weight, power, and thermal envelopes that you guys deal with? I do love the way they ask it in one sentence too. It's
Yeah. How do you balance it? Yeah. Well, so you've probably heard this thing, before, and there are variations on it. Size, weight, power, choose two, right? Or whatever three variable optimization problem you have, choose two, and the other one hits the floor. And that's kind of the answer. When you look at the latest Intel Xeon processors, those are the ones that go on the servers that we also use in some of our products. The power dissipation for the lowest power parts is approaching 300 watts. In the previous generation that we worked with of those server class processors, they were at 125 watts. So humongous jump up in the power dissipation. So how we cool something that's going to wind up being the same size circuit card or the same size box that's got that big increase of power is a real challenge for us, right? And we are at the bleeding edge of dealing with that problem for the industry, right? It's much easier when you're in a data center. You can pipe in some water and set up chillers and things like that. But when you're in the belly of an aircraft at 60,000 feet, you can't just order more air conditioning.
I have 2 questions.
Sure.
My first question is, since Mercury deals with like national defense, a big player obviously in our national defense are our competitors like China. So could you compare like Mercury's chips versus a big Chinese chips manufacture for their like national defense?
Um, yeah, I don't have any insight into the Chinese military industrial complex's capabilities, right? I will say that, what you look at with us is we are taking commercial technology, commercial state-of-the-art technology, and applying it to, these challenging, aerospace and defense problems. And I would expect that the Chinese and our other adversaries are using also commercial state of the art, the best they can get, which may be more difficult owing to export controls that exist in various parts of the world where things are made, to also power their defense solutions.
Okay.
Right.
Quick question. How do you guys ensure security? Because you guys work in defense, right? So
Right.
how do you guys ensure that your chips are secure and that um, like there's no security problems with your chips?
Um, Well, so that's a whole long discussion in and of itself. I will say that this is a problem that the industry has in general. Just like software vulnerabilities in Microsoft Windows or Red Hat Linux. Those are discovered and dealt with, et cetera. The people who are designing the commercial state-of-the-art chips, have these same problems, and have to take these things into consideration. So when you look at the Xilinx FPGA chips made by AMD, you can go you can go find the data sheets and the manuals for this stuff online, and you can find out about all the security features that are incorporated in that. And certainly we incorporate devices like that have intrinsic security features, and certainly security is a criteria in defense applications. So I'll leave that at that.
I have a question here about another challenging topic for especially aerospace and defense, which is the rapid turnover of commercial technologies, balancing against the requirement to be able to supply it for forever.
Yeah, that's a hard problem, right? So, if you go back 40 years, the rate of advancement of semiconductors was slower, right? From generation to generation of the manufacturing technology, it didn't evolve as quick. And and the other thing was, I mean, in the 1970s, 80s, the U.S. Department of Defense was literally the largest purchaser of semiconductors in the world, right? Today, the worldwide defense industry, purchases a number best approximated by zero of the, semiconductors made in the world, right? So as a consequence, they're certainly taking advantage of the latest state-of-the-art capabilities, but at the same time have to be mindful about how you're going to supply these, because whether it's defense or, say, industrial applications, like you might find in electric power distribution, or honestly, like if you're an automobile manufacturer, right, and you're going to make an ECU for 10, 12, 15 years, right? You got to have a supply chain that can sign up to deliver those things for you. And what happens is, in some cases, when you're taking advantage of really commercial things, right? They're getting used, say, in data centers, and every 3 years and it's a new generation. You wind up having to manage your supply chain, and it might be that you're buying a lot of parts that you're just putting on the shelf because you're going to project your demand for the next 10 years for that particular thing that part goes into.
Hi. So my question was, especially with your personal journey, you did a lot of academia, you've done a PhD. How important do you think, like especially nowadays, like with Mercury on the leading edge, is getting a PhD, and like, or do you think there are opportunities today, like if you only got like a bachelor's or like a master's, do you think like how much more different would it be? Like,
So, we need everybody, right? It's a team effort. Most of our employees have bachelor's degrees in our engineering ranks. We have percentage of masters. You got a very tiny percentage of people with PhDs. You know, a, a PhDs in particular take a certain amount of perseverance, or I like to say I have a high tolerance for monotony. And it's not for everyone, right? So, that is a way to go. And if that appeals to you, and, in explaining my journey, I think maybe you kind of understand, what my motivations were or have a sense of them. For you, that may be completely different. So, my oldest daughter, very, very smart. Of course, you're going to say that about your kids, right? And I fully expect her to go to grad school. Like me and her mother. And, she finished her bachelor's degree in electrical engineering and had, a great undergrad research experience in cognitive radio, and then had, a couple of fabulous internships at National Instruments in Austin, Texas. And he said, no, I'm not going to do grad school. I'm going to go work at National Instruments. And that was what was right for her, and it's worked out really well. She got laid off. She got a much better job at Ericsson, the people that make the cell phone silicon, right? And she and her husband live in Stockholm, Sweden now. So they're enjoying the heck out of it. So find what's right for you, and it may be a journey of discovery. You may find that after 4 years of engineering school, maybe you want an MBA.
How much more risk is there involved with working with the military as a semiconductor company, as opposed to being like more commercial and for civilian?
Risk in what sense?
Like operational risk, like change in policy can greatly affect like revenue and that sort of thing, like contracts.
Um, you know, it happens both ways, right? I mean, most of my career, the vast majority of my business was commercial. I had defense applications, but it was really commercial. And, I went through the dot bomb, right? Which, we were very hungry during the dot bomb, especially since we were, right in the heart of selling, IP that was critical to the dot bomb people. We went through the 2008 downturn, same thing as commercial things. I tell you, the commercial companies, sometimes they say, hey, we're going to go do all this commercial stuff. We don't care about defense because it's not that big, right? Those downturns happen, and suddenly all those guys want to do defense because the defense spending is still happening, right? So there are variations in budget and acquisition cycles and all the rest of that that happen in any industry. So I would say, realistically, when you're just thinking about a job, how much confidence do you have? How much basis of confidence do you actually have you're going to have that job in 6 months, right? And I think the reality is, even the people that think they've got the most stable job in the world, whatever it is, whether it's commercial or in defense or medicine, whatever, they maybe have really about 6 months of visibility because things can change. So don't let that change what you do.
So I'm afraid I think that's all we've got time for on the main forum, but please, you're very welcome to come ask the question directly afterwards, and thank you very much.
Thank you. Thank you, everybody, for your time.